Hey, welcome to the next channel. So if you are following my video episodes time to time, whenever it comes to a question of inter-process communication, I often mentioned or suggested you to use socket platform so that it gives an opportunity for you to debug with Wireshark, tools like Wireshark and stuff like that, and more precisely when you are using it for some kind of control systems within the same many processes within the same system. Still it is highly advisable to use sockets for many occasions. But having said that, you can also use other mechanisms like message queues, and as well as in this episode I'm going to discuss about shared memory. So each has its own advantage, but personally, if you ask, sockets can be used for a wide variety of applications. And moreover, as I said also in my previous episodes, the main advantage of socket is also in case if you suddenly split that specific processes between multiple systems, like a sort of distributed computing architecture or something like that, you can suddenly split very easily, because this IPC, whatever you are communicating within the same system using a local host, all you need to do is just point it to a different system and it is going to work more or less seamlessly. So this is the advantage of using sockets versus you start architecting your solution with message queues, or even in this case like shared memory. So I suggest you to watch a couple of my episodes research I have done with message queues versus sockets and the overhead, and also recently I have shot an episode on IPF in the context of performance profiling with network subsystem of a Linux system. So when you do profiling with tools like IPF, it profiles, you can check the overall system performance of a given hardware. So I highly recommend, when you are watching this video as a part of research standpoint, you will get that big picture if you go through those videos. So coming on to the topic, what I have done is I have done two sample user space programs. As you can see here, it's a simple C code, and with that I can demonstrate a simple shared memory, so that you can use this shared memory as a IPC mechanism. And if you see, you need a shared memory between multiple threads. Of course, any global variable is going to do the same, because global variable is going to be the part of the same address space of that entire process, and any number of threads within the same process is going to share the same address space. So that is something you don't need to worry about. But if you have multiple individual processes, then you need a stranded IPC, and in that you can think using something like shared memory in case if it requires, because shared memory can give you a high performance compared to sockets, because sockets is going to add the overhead of networking subsystem within the Linux kernel. You should understand whether you use shared memory, whether you use pipes, whether you use message queues, whatever it is, you are at the mercy of Linux kernel. It's just the kernel giving you the platform to do so, because you as a user space application developer, you are at the mercy of Linux kernel. The kernel provides that platform, you are just using that platform, and on top of this platform you are building your applications on top of the same. And please understand, any IPC is just adding a door to your room or your house, and not to glorify and not to think it's a huge some sort of huge phenomena or something like that. Any IPC is very simple. You are just adding an interface like this window behind me, or else a door over there. So it's just as simple as that. It's just an interface between one entity to other entity, and this interface, it's something kernel provides, so that you can make use of these features provided by the kernel. If the kernel doesn't provide, of course you don't have any option at all. So it is just a feature provided by the kernel, so that one process registers the same, the other process also registers to the same, and when it comes to sockets, you tell which port you are listening, and other client application will connect to that remote port and it sends the data. Similarly, if you think about shared memory, it is quite very simple. You have various APIs with which you can register a shared memory, and then you can access this shared resource, memory resource, between multiple processes. As simple as that. So you can see here I have two applications. One is a writer and a reader. Because this is not like a socket programming, you have some client and server, you have something listening over there or something like that. Both have similar hierarchy. The objective is you have two processes having a shared resource, as simple as that. So we go through this writer, and then we can go through this reader. So you can see here it is a very simple code. I have this all the include files you can include. This is not any multi-threading or something. You don't need any pthreads or any such complicated stuff. So you can see here, if you come down, we can for now ignore this F2K. If you see here, you are getting a shared memory resource, and you are getting this ID, which is like a file descriptor, and if this ID is less than 0, it may have some kind of error code. You can do as just man page of SHM get API, man SHM get. You can see here, as a part of errors, it has various error code. You can check whichever is a specific error code you want to handle in a full-fledged application. Please bear in mind, like I say in most of the episodes, the code what I show is more represents a real-world use case, but you should not, as it is, take and put it in a production system without doing the actual modification. So you need to modify as much as possible according to your specific application, and then you can integrate into your applications. So you can see here SHM get, and we need a specific key, and this is quite optional. You can use this F2K, and then you can derive a unique key, or else without that you can use even an arbitrary value or something like that. So you can just do the same. In my example, I am using this API, so that's what is this API does, F2K. Again, you can do a man page, or you can read about it online if you need more information. So this is a very simple API. You can use the same, and you get that key data structure, key underscore t key data structure. So you just need to pass over there, and then you can mention what is the size you want. SHM get, once again, if you do a man page, you can see here the size and then the SHM flag. So we are using the same, and we are giving the permissions, and we are mentioning as IPC create. So as simple as that. So in our example, you can see here we are creating a shared memory space around 1 KB, so which is 1024 bytes. And if it is the file descriptor is less than 0, and we are showing the error, and we are coming out, and if it is not 0, if it is not any error value, then it is going to continue. So with this, the shared memory file descriptor is created, and what we need to do is we need to have a pointer or a buffer which is which we are supposed to link to this shared memory resource. So if you see here, it is a simple unsigned char star buff. Like you create any buffer, and you have other options. If you have a static allocation, you will be doing unsigned char buff of 1024. So in this way you can create an array, and if not, you can do this way, and you can do a malloc and other stuff, right? So you can do a malloc, and you can create you can assign a memory resource. So either way, what happens is this, if you do, it is going to be restricted to this process, and our objective is to create a shared memory space. So if you don't do that, of course the memory space will be restricted to this process. So that's what it is. So we can't use either of that, and what we are doing is we are creating a pointer, and to this pointer we are allocating or else we are just linking this pointer to that shared memory resource which we just created. So what we are doing is with this API SHM attach, you can see here SHM stands for shared memory attach, and we are passing this file descriptor, and that's about it. So we are attaching this buffer pointer to that shared memory resource which you just created. So that's about it. And after that, like any buffer, you can access the same, and provided you should understand this is the size of 1024 bytes. That's about it. So you know the boundaries, and you can access it like any memory allocated space. So inside, what I'm doing is, as a simple example, I'm doing a memset of this buffer, and I'm doing it for first 10 bytes. I don't need to do for all 1024 bytes. So I'm just doing it for 10 bytes, and I'm just doing a debug print here. You can see here printf, and I'm printing this iteration. It is in each iteration, I is going to have a different value. So all the 10 bytes is going to have a different value after every iteration. So what I'm doing is, in this for loop, I'm just printing this raw bytes. So assume using this shared buffer, you can pass a network packets. Of course, you can do that without socket programming. You can have any sort of custom protocols within the same. I can see various applications. You can of course share any memory mounted file system or anything like that. You can do anything as the way your application needs. So being myself a networking guy, I see a lot of possibilities. I can even do some kind of how to say, I can do a sort of network communication stuff happening between two processors using this shared memory as well. So a lot of things you can use. As I said, its overhead is going to be lesser than you use a full-fledged socket, but being myself a mundane core networking developer or an expert, I like generally sockets because it is okay to deal with the overhead, but you get that guaranteed platform which really works well, and it has a very good debugging mechanism. Here, if something you screw up, it is going to prove difficult in a sort of production environment code. So that's what it is. You need to be very careful because you are accessing the raw memory. You can do any mistakes, although it's a virtual memory. So that's about it. So I'm printing this bytes, you can see here, and after each iteration I'm waiting so that you can just tap a button on a keyboard and it is going to repeat this loop, as simple as that. So with that it is done, and once it is all done, we can do a detach of that buffer or that pointer. So it comes out and it releases that specific linkage. So this, if you see here, SHM-DT is the actual opposite API of this SHM attach. So this attaches that pointer to that memory resource. SHM detach, it is going to detach it from that memory resource. So that's about it. So SHM attach and SHM detach is going to be like opposite APIs. One is to attach and one is to detach, as simple as that. So you should notice we have created this memory resource and we are not destroying it, or else we are not unallocating the same. So that unallocation part, I'm doing it in the reader. You can go through this code. As you can see here, this is the reader, and this is going to have more or less the same code. You can see here the first 3 lines are the same, and we are getting this SHM ID, and then from SHM ID we are getting this buffer we are attaching to that file descriptor or that shared memory. So with that, our buffer is ready, and in this case what I'm doing is I'm running an infinite loop so that it sort of polls that memory resource. So it polls again and again after every few seconds. You can see here I kept sleep of 2. So after 2 seconds it is going to poll that resource, and in any case if there are any changes, it is going to display onto the screen. You should notice I'm not discussing about any sort of synchronization. You may get into some kind of trouble, so you should keep in mind to use some kind of synchronization, because it is not that safe to do this way. So having said that, so you can see here we can anyway walk through the code so that it gives that good it gives that good understanding that what is exactly happening behind the scenes. So you can see here I'm just doing an entire buffer dump, just like I have done in this SHM writer. And once it is all done, you can even do, or else we can restrict it to X amount of iterations, and once it is all done you can do a detach, and then you can actually destroy the share memory. You can see here SHM control, and then you can pass the parameter as to destroy or else to free that memory resource. So this is similar like you do malloc and then you do a clean of that as well. So that's about it. What we can do is we can go back here and we can compile and we can execute the same. So I wrote this compile script. As I say in all the episodes, I don't like much make files. So this compile script does the job. You can see here there are some couple of GCC commands and then it is going to compile the same. So you can see here it has been compiled. We got our binaries. So what we can do is we can run our SHM writer. And you can see here it has ran that first iteration and it is staying over there. So since it is starts from 0, I is from 0, it is dumping this 0 byte values. So you can see here. So you can go here and then you can run SHM reader. You can see here since it's an infinite while loop, it is going to read the same values over and over again. So it is just dumping that buffer contents of that first 10 bytes of that 1024 bytes of shared memory resource. So it is doing the same. So we can press any key here so that it goes to that next iteration. So you can see here the next iteration, the I value of I is 1. So it is just showing the same. And you can see here now the buffer contents have been changed because since it's a shared memory resource, you do over there in that process, it is going to reflect in this process as well. So that way if I do a couple of iterations, it is going to show the changed value over here, since I did it quite fast, whereas in this reader there is a delay of 2 seconds. By the time it has gone to value 4, you can see there. So since I have pressed enter key quite fast, it has iterated to other values 2 and 3 and then it has jumped to this 4. So reader is currently reading whatever it has been set by that writer at this point of time. So that way, if I just iterate it for some time, the entire writer is came out of that loop. You can see here it has ran around 10 times or 10 iterations. So the last value is 09. So here we can able to see the last whatever value it has been set. So once again you can see since I have done quite fast, after 4 it has jumped to 6 and after 6 it has jumped directly to value 9. So this really demonstrates the way shared memory resources work, and it is quite useful. As I said before, it is quite less overhead when it compares to something like a socket, because you need the entire networking subsystem to make sockets possible. It is just not IPC alone, it is all about the top layers which really matters. You have this, if you do via IPv4 UDP or TCP, you have this entire TCP IPv4 network stack whenever you do sockets, versus a platform like this is quite lightweight. It is quite like message queues, it is very lightweight and it is good to go. But having said that, message queues, as the name says, it itself denotes you send a message from here to there, one location to the other location, just like sockets, but without any memory, without any networking a layer on top of it. So that's what is message queues. But when it comes to shared memory, as the name says, you are using a shared memory resource between two processes, which is not possible by using some global variables, because if you do use a global variable, it is just a variable within that process memory space. So that virtual memory space, it is just going to be a memory space within that process. So long back I have even done some picture. Let me just pull the same. I have done some architectural picture so that you can get some good idea. Yeah, you can see here I did the same in DIA, and let me just show its render. So you can see here this is the picture. So this is how it illustrates. You have multiple processes, user space application processes. Each will have its own surrounded memory space, and whatever you do, it is all within this memory space. And of course you need some mechanism like IPC so that you can bridge between this memory space to this memory space. And when you do use platforms like message queues and network sockets, it is like sending data from one location to other location, like communication of bytes from one place to other place, versus if you use a platform like shared memory, it is just, as the name says, you are using a common memory space, so that any process whichever is using the same, it can use this shared memory resource. So as an experiment, we can also do one more thing. We can run one more instance of SHM reader. You can see here there is nothing wrong in running the same. So both are going to run. You can see here both are running. So this confirms both are running. And once again, if you invoke this writer, it is going to populate these bytes. And you can see here from 9 it has changed to again value to 0. So because the writer has refreshed that buffer and it has re-put that new bytes, the first iteration, which is 00. So you can see here both these instances are showing us these new changed data. So if I iterate one more time, it is going to show the value 1 1. So this is the advantage it is. So if you have shared memory resource, any number of processors can use this as a common shared memory resource pool, and then they can communicate seamlessly. This is not something possible with network sockets, because it is just 1:1 communication. Same way message queues, as the name says, it is sending messages from one place to other place in a way like IPC. Of course it is IPC. So that's about it. So hope this video gives that big picture. As I say always in my episodes, I focus how these concepts have been used in the real time applications, in the real industry use case. So if you see, this is the use case of shared memory. It is just not writing some, if you generally search in internet, they give some reader writer or client server code for in the case of sockets, or in this case a reader writer or something like that. But it is not just about writing some sample code here and there. The objective is, in the real world use case, at which situation you should use message queues, at which situation you need to use sockets, at which situations you can give up, do away with the sockets and you can use something like message queues. Usually people prefer message queues to avoid the overhead of sockets, but if you ask me, than that you can still stick with sockets. You are not going to have big overheads unless until you are using it for some gigabit speeds or something. You are using it for few packets or few messages here and there in a minute or in a second. It is just not going to impact much. So they may have certain conceptual ideas what they have got it around a decade back of that limited hardware, but if you ask me right now, any hardware you use, it is powerful enough to do that basic message transfers. It is not going to be a big overhead unless until you do it at some gigabits rates. So hope you guys loved watching this video. As I do with most of my episodes, I'm going to bundle this code, and I'm going to share you that tarball of that source and as well as the compile script, so that you can download, you can customize, and you can use it in your applications. And in case if you are using it for a production system, make sure that you further customize the same, add some sort of security on top of it. Security, I don't mean like I mean to say security means add some protection code on top of the same, so that you can check if anything goes wrong, you can handle that error cases, and you can gracefully exit and show the errors or handle those errors. So I have not done the same, as you can see here. So do those changes, and then it is good to go to be used for any production usage. Otherwise, just take it as a learning curve, add some code on top of it, and you can do further experiments. You can write even network protocols communicating through shared memory platform, or else you can do some kind of file config file or something. You can have a specific process opens that config file and it keeps it in this shared memory resource. The other child processes, I don't mean to say that fork and then get child process, other processes, individual processes like what you see in here, okay. These reader processors can take this and then they can get the contents of that config file without themselves opening it once again actually. So all these things are possible. So with this I would like to wrap this episode. If you have anything to discuss, be in touch via mail. Thanks a lot for joining me. Stay tuned. Have a nice day. Bye bye.